You recall that when you had a periodic impulse train in the case of Fourier series, we found that all Fourier coefficients are the same magnitude. So, let us now take an impulse and see just one single impulse, this is of course a periodic, and see what its Fourier transform would look like. So, f of t is taken to be a delta function. So, you have a unit delta sitting at t equals 0, that is a Fourier, that is a time function. The Fourier transform for that f of j omega with minus infinity to plus infinity, the function of time is delta t e to the power of minus j omega t dt. And since we have a delta function in the integrand, naturally the value will be the value of e to the power of minus j omega t at t equals 0, that is equal to 1. So, we have a very nice and compact result that f of j omega equals 1, which means the Fourier spectrum that. So, you have an impulse, you have a Fourier spectrum which is flat. So, we can say now this particular pair of transforms this delta t has a Fourier transform which is equal to 1. That means the coefficient density at all frequencies ranging from minus infinity to plus infinity equals 1. Very nice and useful result. Let us take now a more complicated example. E to the power of a t cos omega c t u t. That means the time function would be something like this, which is an oscillating a sinusoid, but with decaying amplitude. Now, this can be written as 1/2 of e to the power of minus a t e to the power of j omega c t plus e to the power of minus j omega c t u t, which is 1/2 of e to the power of minus a plus j omega c t plus e to the power of minus a minus j omega c. So, this decaying exponentially decaying sinusoid can be thought of as two exponential functions of this type. And in the very first example, we observed that e to the power of minus a plus j b t can also have the same type of Fourier transform as when you had e to the power of minus a t 1 over j omega plus a. Instead of 1 over j omega plus a, you have 1 over j omega plus a plus j omega c in this case. So, the Fourier transform for this will be half of 1 over the Fourier transform for this particular function. Of course, this will also have u t because that continues, j omega plus a plus j omega c. That is for the first function. The second function you will have 1 over j omega plus a minus j omega c, and these two can be combined, and together you have an expression which looks like this: j omega plus a over j omega plus a whole squared plus omega c. Likewise, you can plot the spectrum, and then you will find that around omega c you have some kind of peaks, but we do not do that. Similarly, e to the power of minus a t sin omega c t u t can be shown to have a Fourier transform which is equal to omega c over j omega plus a whole squared plus omega c c squared. right. And a last example, if I have a function like this, a t upon 2 minus d upon 2, this is f of t. So, it is a pulse in the form of a triangle lasting from minus d upon 2 to plus d upon 2. It can be shown that this will have a Fourier transform which is equal to a d upon 2 sin omega d upon 4 by omega d upon 4 squared. So, this is something like sin theta by theta type of arrangement, but squared. That means the decay is faster. So, the spectrum for this would be like this, and this I will leave it for you as an exercise to show. Now, all the functions that we have taken so far are nice well behaved functions which have the property that all functions considered so far satisfy the relation from minus infinity to plus infinity f of t dt converges. That means the magnitude of the function is integrable from minus infinity to plus infinity. That is why we have an exponentially decaying function, an exponentially decaying sinusoid here, a pulse which lasts for a finite amount of time, either a rectangular pulse or a triangular pulse, an impulse which can be integrated, that is equal to 1. So, all such functions we have considered nice properties like this. This property excludes some desirable functions for which we should like to find Fourier transform. For example, u of t lasts from 0 to infinity, sin omega c t u t, a sinusoid cos omega c t u t. Functions like this are important and we come across them quite commonly, but in the classical sense these functions do not satisfy this property. Therefore, we do not find the Fourier transforms for this, not yet anyway. In the classical Fourier transform theory, these functions were excluded from the scope, but now that impulse functions have become a matter of common usage, once we have impulse functions we should be able to find out the Fourier transforms of these functions as well, which we will do a little later. The mathematical justification for such usage comes from what is called the distribution theory, which has sanctified the use of impulse functions and the related mathematics. We will not however go into that, but nevertheless we will assume certain relations which are sanctioned by the theory of distributions and use those results to find out the Fourier transforms of such functions as well a little later. But before that we would like to have a closer look at some of the properties of the Fourier transforms in order for us to get some familiarity with their characteristics before we move on to finding out the Fourier transforms of special functions of this type. So, what we would now like to do is discuss the properties of Fourier transforms. These properties will run somewhat parallel to the properties we discussed when we talked about the Fourier series. After all, Fourier's integral and Fourier series are related to each other. Therefore, it is natural for us to talk about properties which are similar to what we discussed in the case of the Fourier series. So if f of t is even, then it means that f of j omega is real. So when you substitute j omega in the Fourier transform, it turns out to be real. Example, what we have seen, this pulse. This is an even function, and then we found that f of j omega is real. There is no j term in the f of j omega. If f of t is odd, then it turns out that f of j omega will be imaginary. There is a j term sitting outside. We will take just give an example, which I will not, however, derive that. Let me write this. This is a, this is d. We know this is ad sine omega d upon 2 divided by omega d upon 2, because I am repeating this again and again because this comes so frequently that it is better to remember that. Now suppose I have a function like this, a d upon 2 minus d upon 2. This is certainly an odd function. We have a pulse of value a lasting from 0 to d upon 2 and minus a lasting from minus d upon 2 to a. Its Fourier transform turns out to be minus JAD sine squared omega d upon 4 divided by omega d upon 4. So you observe that this is immediately a j sign attached to it, so it is purely imaginary. The proof of this is straightforward. If you write the expression for f of j omega as minus infinity to plus infinity of f of t cos omega t dt minus j times minus infinity to plus infinity of f of t sin omega t dt, we recognize that e to the power of j omega t is cos omega t minus j sin omega t. So we split up the defining integral for the Fourier transform into two parts like this. Now if you call this integral I1 and call this integral I2, then we notice that if f of t is even, the product f t cos omega t is also even. Therefore we are integrating, as far as I1 is concerned, between two symmetrical limits. So whatever sequence of values this integrand takes from minus infinity to 0, it takes from infinity to 0 as well. Therefore the integral I1 will be twice the value of the integral from 0 to infinity. On the other hand, I2 involves f t times sin omega t. Therefore that is an odd function of time, and we are integrating between symmetrical limits. Therefore the value of the integral from minus infinity to 0 will be exactly the negative of the integral from 0 to infinity. So as a consequence, I2 is 0 if f of t is even. Similar arguments will show that if f of t is odd, f of t sin omega t is even. Therefore the second integral will be non-zero, but the first integral, which involves f of t cos omega t, that turns out to be the integrand is odd. Therefore if f of t is odd, f of t cos omega t is odd, and you are integrating between symmetrical limits. Therefore I1 will be 0 if f of t is odd. So we have the situation that if f of t is even, then the second integral vanishes and the first integral I1 is real. Therefore f of j omega itself is going to be real. On the other hand, if f of t is odd, the first integral vanishes and I2 remains, but I2 is preceded by a j. Therefore f of j omega will be purely imaginary. Let us now discuss another property of the Fourier transforms. Translation in time. If f t has Fourier transform f j omega, then f of t minus d, that means you delay the signal by some amount, then this turns out to be f j omega e to the power of minus j omega. This is a very useful result. If you delay this time signal by d units, the Fourier transform gets multiplied by e to the power of minus j omega d. It means the magnitude of this being equal to 1, the Fourier transform magnitude will remain the same, but the phase will be disturbed by an amount minus omega d. Very similar to what we had in the case of Cn coefficients in the Fourier series. The proof is quite straightforward. To find the Fourier transform of f of t minus d, all you have to do is from minus infinity to plus infinity, f of t minus d e to the power of minus j omega t dt. This is the defining relationship for the Fourier transform of f of t minus d. Now what we have to do further is quite evident for you. All you have to do is bring it. We know that minus infinity to plus infinity of f of t e to the power of minus j omega t dt is f of j omega, capital F of j omega, from this. Therefore, we have to bring this into that form. So all you have to do is put t minus d as x. Then f of x e to the power of minus j omega t plus, instead of t minus d is x. Therefore, t is equal to d plus x. And then dx you get. And then you have e to the power of minus j omega d term coming outside. Then you will have minus infinity to plus infinity of f of x e to the power of minus j omega x dx, which is indeed f of j omega. So it can be shown that this is equal to f of j omega e to the power of minus j omega d. Very, very, very useful result. Extremely useful result. As an example, simple example I will work out. Suppose I have a delta function here of unit magnitude sitting at time t equals 2. That means this is delta t minus 2. And we know the Fourier transform of delta t is 1. The Fourier transform of this is e to the power of minus j to omega t, 2 omega. That's all. Because you have to multiply the Fourier transform of delta t is 1. You are multiplying this by j minus e to the power of minus j omega d. The delay is 2 seconds. Therefore, e to the power of minus j to omega. We'll work out some more examples in the next lecture. But before that, let us now summarize what we have done today. So in this lecture, we started with a review of the Fourier transform defining integral and the inverse Fourier transform. Then we constructed the Fourier transforms of a few typical time functions. Specifically, these are the impulse function, the rectangular pulse function, the exponentially decaying sinusoidal function, a triangular pulse function, and we observed that if the Fourier transform turns out to be turns out to be real, then there is no necessity for us to plot the magnitude spectrum and the phase spectrum separately. Because the entire function is real, we can exhibit this by means of one single spectrum which represents the value of f of j omega. We also introduced ourselves to a new function sinc x, which is defined as sin pi x over pi x. Sinc x has the value 1 at x equals 0 and vanishes when x takes integral values like 1, 2, 3, minus 1, minus 2, minus 3, etc. So this new function is helpful in depicting the Fourier transforms of pulse functions. Then we took up for study some important properties of the Fourier transforms. The first property we studied is that if f of t is even, then f of j omega is real, and if f of t is odd, then f j omega is purely imaginary. So we also saw that, we also mentioned earlier that if f of j omega is real, then the magnitude spectrum and phase spectrum need not be exhibited separately. They can be exhibited by one spectrum which gives both the magnitude, and phase of course will be either 0 or 180. Same thing can be done if the spectrum is purely imaginary. In that case, we plot f of j omega by j. That means the imaginary part of f of j omega can be plotted by means of one spectrum, and because the real part is 0, we can also do that extend this principle of having only one spectrum even if an f of j omega is imaginary by keeping at the back of mind that whatever values which we plot on the spectrum are purely imaginary quantities. The second important property that we studied was that if the function f of t is delayed by tau seconds, then the Fourier spectrum gets modified, the f of j omega gets multiplied by e to the power of minus j omega tau. That means the new function will have the same magnitude spectrum as the earlier function f of t, but the phase will be modified. This is not surprising because we saw a similar result in the case of the Fourier series where the Cn coefficients, the magnitude will remain undisturbed if the periodic function is delayed by a certain amount of time, say tau seconds. Only the phase will get modified. After all, f of j omega is closely related to the Cn coefficients, therefore we have a similar result here also. We will stop at this point and continue our discussion of the properties of the Fourier transforms in our next lecture.